Hey everybody, in this section what we're going to do is we're going to take that limit definition of area that we talked about in 5.2 and we're just going to give it some special notation. And the notation that you're going to see involves what we call a definite integral now. Now, just because you're going to see an integral symbol like you saw before does not necessarily mean that what we're doing in this section really has even any connection to doing the antiderivatives that we did before. Now eventually that will be the case, but in this section, let's just think about the definite integral as being our formal notation for the definition, for the limit definition of area. So as we saw in the last section, if a function is defined on an interval from a to b, then we can describe the net area, and this is how I wrote it out. This is how the textbook a lot of times will write it out, but this is how I wrote it out. We can define the net area bounded by the function in the x-axis as the limit as n goes to infinity of the summation, I going from 1 to n, b minus a over n times f of a plus b minus a over n times I. And as we saw when we did the limit definition of area, this is simply summing this is the base times the height of an infinite number of rectangles, or of rectangles that have an infinitesimal width. And that's kind of what this definition over here is doing. This is still like the base and the height of all of the rectangles, but what this is doing when it's saying delta is going to 0, it's saying the width of all of those rectangles is going to 0. So you can say the limit definition of area as we did, or you can say it through this definition. Now, what we do though is we take this definition that we worked with and we say, instead of writing things out like this, we are going to write them this way, because we're going to say f is integrable on the interval ab, and so we will write the integral, the definite integral of f of x going from a to b. And so that's much cleaner looking than this right here, but it says the exact same thing. So when you see a definite integral notation, and I'm going to say this a ton through these videos in this section, it means what is the net area bounded by the function in the x-axis between x equals a and x equals b. That's exactly what we were doing here. Now you'll notice that I'm saying it's the net area, and I'll talk a little bit later about that, but essentially what that deals with is, I mean, you can think about this. If you're evaluating functions, whether it be in here or here, and you're using the evaluation of the function as the height of the rectangle, you can imagine in some cases, if your function's below the x-axis, that the heights of those rectangles are kind of negative in a sense. And so essentially what this does is it subtracts any area that's below the x-axis. And so like I said, I'll talk a little bit more about that later in these videos, but it's really important that we understand that both that limit definition equation as well as this new notation, the integral of f of x from a to b, refers to the net area bounded by the function in the x-axis from a to b. And we do call this the definite integral. And also, like I said, at this point, don't try to connect this to what we did before with antiderivatives. Just think of the definite integral as the notation that we're using to describe the area bounded by a function in the x-axis from a to b. Okay, so with all of that said, and I think I've also mentioned this to you before, that the integral symbol technically means sums, or taking a sum, just like sigma notation means. And so when you see this elongated s here, it's essentially just replacing that sigma. So the emphasis in this section is simply grasping this concept of the new notation, and then also getting familiar with certain properties related to definite integrals, but that's just certain properties related to net area. So in these first few examples, I say express the area of the following shaded regions as a definite integral. Well, you can see in this picture that what I've got is I've got an area bounded by a function, y equals 4 minus x squared, and the x-axis, and it appears that this is going to be -2 and this is going to be +2, because I think those would be the x-intercepts for this function. So in terms of a definite integral, this would be the integral of 4 minus x squared going from -2 to 2. Now, to be completely accurate, what we do is we put this dx in there, because that is the width of all of our rectangles, and remember that's kind of infinitely small. And I know it's dx in terms of antiderivatives, when we covered this back in 5.1, was a little bit different. It referred to the variable of integration, and it's actually doing the same thing here. See, all of this stuff is actually going to come together in section 5.4 when you learn the fundamental theorem of calculus. But right now, I just want you to know, when you have a function and it's, you're looking at an area bounded by that and the x-axis from a to b, we write it as the definite integral from a to b of that function and then dx. So this one would simply be the definite integral of absolute value of x dx going from, you could see, -2 to 3. Or this one right here would simply be the definite integral of the root of 16 minus x squared dx going from, I think that's going to be -4 to +4. Looks like this is a circle with a radius of 4. Or at least I shouldn't say a circle, it'd be a semicircle with a radius of 4. So -4 to 4. So all of these definite integrals are it's just the abbreviated notation for capturing the area bounded by a function in the x-axis from x equals a to x equals b. In terms of this notation that the text sometimes uses, you should be able to take things like that and then express those as definite integrals as well. It's actually, I think, just as easy. I mean, you can kind of see what your, this has a function and then essentially your dx. So here's your f of x, and then this is like your dx, and you've got your a and your b. So if you were to write this limit as a definite integral, it would just be the integral from, you can see your a and your b are -2 and 4. The integral from -2 to 4 of the square root of, it'd be 5x squared minus 1 dx. And here, let me clean this up a little bit because that looks a little sloppy. So -2 to 4. So that's it. You're not going to see a ton with this. My emphasis is this net area equation, but then, moving forward, my emphasis is going to be on, can you appropriately capture the net area bounded by a function in the x-axis from a to b? And that's kind of what we're doing in here. Now, like I was saying a little bit earlier, a limit of sums can represent many things other than area under a curve, some positive, some negative, or some 0. Said sketch some graphs that would result in each of these probabilities. So you could feasibly come up with a graph where, maybe this was the net area that we were trying to capture. So here's the area between a function and the x-axis between x equals, it doesn't even matter. Let's say that this is like x equals 0 and x equals 4 or something like that. And so in this case, if we did the integral of the function from 0 to 4, if this area up here, let's pretend that that area is 1 and that this area is also 1, the total area is equal to 2, but I'm not asking for total area when I give you the definite integral notation. So a limit of sums, which is what this is, remember this is the same as the limit definition of area from up above, so a limit of sums is not simply the area, it's the net area. And what is the net area in this case? Well, you've got an area of 1 up top, but then you've got an area of 1 below. So the net area ends up being 0. And so we see this often. And we have to recognize that when we're doing these definite integrals, that it is adding any areas that you have up top, but then it's subtracting those areas on the bottom because the f of x is negative. The heights of those rectangles are negative. So if I drew a picture like this one right here, if I said, let's take an area like this, and then we've got it just a little bit below the x-axis. You can imagine in this case, isn't this area above the x-axis much more than this area below the x-axis? And so this would be a positive definite integral. Whereas if I drew something more like this, where it was kind of the opposite, and we're looking at the area bounded by the function in the x-axis, and we have this region, and then we have this region down here. All of these rectangles have positive amounts that are added to our total, whereas all of the rectangles that would be down here would end up having negative areas. So the net effect would be a negative result. So you could have a definite integral that is equal to 0. You could have a definite integral that's positive. You could have a definite integral that's negative. And again, it's because definite integrals are capturing the net area bounded by a function in the x-axis from a to b. Okay, in the next video, I'm going to walk you through the second part of the notes here, which are just some basic properties of these definite integrals.